Morning. I'm Spot on Weather meteorologist Matthew Euler. Welcome to a very special video today. I am going to be covering memorable East Coast winter storms. Now, I know all you snow lovers will appreciate this video. Um, we've noticed with a warming climate how things have changed. It seems as if winters are starting later and lasting into the spring now. We're seeing a shift in the winter season. We're seeing major changes with the frequency of major winter snowstorms across the eastern U.S. For example, last year was a very scarce winter season for snowstorms in the east. I just wanted to really break down some of the past memorable East Coast winter storms. I'm going to start with an overview of the favorable synoptic weather pattern to produce East Coast winter storms, specifically snowstorms, and then I will go into the specific events. This is a great picture to start things off today. Look how high the snow is. I mean, when you can make an archway to walk on this sidewalk, you have to pile up all the snow over in this location here. This is impressive. This was an impressive snowstorm here. So I just grabbed this picture. When you were a younger kid, maybe you're older now, and when you're younger and you lived in the east, maybe you experienced mammoth snowstorms like this. But again, they're becoming few and far between. Actually, it seems with the warming. All right, so let's go right into the overview of today's video. I'm going to start off with a look at favorable weather patterns for East Coast winter storms. And then I will then transition into a look back, memorable East Coast winter storms. And I'm going to go back to the year 1979. I'm going to start with the President's Day storm of 1979, and we're going to run that to present time. All right, so a couple of the favorable weather patterns, and a lot of this for East Coast winter storms, a lot of this I got out of the Northeast winter storms, the Northeast snowstorms book by Louis Uccellini, as well as Paul Cosin, which is just a tremendous, great resource. And so what we're looking for East Coast winter storms, snowstorms in particular, is we want a long wave trough situated over the eastern seaboard where we get a dip in the jet stream. So we're getting colder air coming down from Canada. The second main piece or ingredient we're looking for these East Coast winter storms is an approaching 500 millibar shortwave trough. And out ahead of that trough, we see typically an area of what's known as positive vorticity advection, PVA. I will show you some of the graphics associated with some of these bullets in the following slides, so just bear with me as we kind of go bullet by bullet down the line here. But you want that 500 millibar shortwave trough, this PVA, superimposed over a surface frontal boundary to kick off some sort of surface wave cyclone development. Now, I remember when I was going through a meteorology school in the past, one of the biggest things that were always drilled into our heads was where's the shortwave trough at 500 millibars? Is it a major shortwave trough or a minor shortwave trough? So in other words, a major shortwave trough, does it show up at the 500 millibar level? Does it show up at the 700 millibar level? With a minor shortwave trough, perhaps it's just showing up at one level, not multiple vertical levels of the atmosphere. And so Pedersen's rule was a big rule that was drilled into my head when I was learning meteorology as a student. How you get approaching 500 millibar shortwave troughs moving over a weak or stationary frontal zone, and this area positive vorticity advection kicking off surface cyclone development. So that was a key rule of thumb there. Now, upper level divergent quadrants of a jet streak, that also matters. I coined the terms left front portion of the jet streak and the right rear quadrant of the jet streak. The left front and right rear, these are the favorable areas for upper level divergence and removal of mass over the top of a developing surface cyclone. Merging of northern and southern stream jet streaks is also a very important feature in some of the most intense or explosive cyclogenesis episodes. When you get both the northern and southern stream jet streams kind of merging, the polar front jet streak with a southern or a subtropical jet streak can result, when you overlay those two jet streaks on top of each other, can result in explosive removal of mass aloft and upper level divergence. So you're removing more mass over the top, which allows your low-level convergence to get stronger or increase in the low levels, resulting in more vigorous upward vertical motion or lifting of air. A strong subtropical jet stream as well is needed, which we see typically during El Nino winters, which provides copious amounts of moisture, overrunning moisture over the colder air at the surface. That's an important ingredient as well. And then at the surface, you want a strong 1030 millibar plus surface high pressure system. Now, the stronger this high pressure system is, the better, because that is going, basically when we talk about temperature in the atmosphere, the colder the temperature is, the greater the pressure, the greater the density of the atmosphere. So the stronger the high pressure systems to the northwest over the Great Lakes and eastern Canada, the better, because that means we're going to have some nice cold air funneling in from Canada into the mid-Atlantic, into the northeast. Additionally, what we look for is what's known as a very strong temperature gradient, or a large temperature difference between colder polar air over the land areas and warmer overlying air over the Gulf Stream ocean current. There's a major gradient that sets up. We end up getting the development of a coastal front between these colder land areas and the warmer Gulf Stream over the western Atlantic. A lot of times what we'll see preceding major winter East Coast snowstorms is a cold air damming situation where we get the clockwise flow around these strong surface high pressure systems, and we get cold air basically to bank up or dam up against the east side of the Appalachian mountain range. And so we have the cold air in place over the land, and then we have, again, that overrunning moisture. So we want that very strong gradient to exist. And that's really what the storms use to intensify, is strong thermal or temperature gradients. All right, so now let's break these down a little bit more now graphically. I've covered these via bullet forms and text format, so now let's break it down a little bit better here. All right, so one of the more favorable signatures for a major East Coast winter storm would be a negative North Atlantic Oscillation, NAO. This is an example on the left from NOAA of what the upper air pattern at 500 millibars looked like in the winter of 2009-2010. And then the blue coloring here is the surface temperature anomalies, blue indicating below normal temperature anomalies at the surface from the northern plains, Midwest to the East Coast. So what we have when we look at synoptic patterns is we have a strong blocking high, generally in the vicinity of Greenland across the North Atlantic, in association with a negative NAO. We have a trough that extends back towards the southwest. In a lot of cases, what we'll get is the presence of a 50-50 low, 50 degrees north, 50 degrees in that area here, 50 degree latitude here, a low here, 50-50 low. All right, so we have a blocking high. So what happens is the storm system develops, it cannot readily escape out to sea due to a blocking high upstream. And this negative NAO tends to favor colder temperatures beneath much warmer temperatures to the north. We have a trough again located along the eastern seaboard. We have an expansive blocking ridge here to the north. Storms generally move up the East Coast in the scenario. Now, this bottom right graphic is just showing you the jet stream configuration. This goes back to bullet one here. We want that long wave trough over the eastern seaboard. We want that dip in the jet stream, the polar front jet stream, to come down. And if we get a nice little subtropical jet here, a strong subtropical jet could actually merge and form explosive storm development, really get storm development going off the southeast coast, and then it'll work its way up off Hatteras, up off New England. See this blocking high to the northeast again? This is not going to allow the storm to go out to sea, because low pressure generally tends to seek the path of least resistance, and that path of least resistance for low pressure is it's going to seek out lower pressure, the greatest pressure falls. That's the path of least resistance for low pressure system. It's never going to go towards high pressure. And I like to use the analogy of, okay, if you're on a bike, right? If you're pedaling on a bike, and you have a choice to go downhill or go uphill, which path are you going to choose most likely? Many people riding a bike are going to choose to go downhill because it's going to involve less energy. So the high pressure here, this blocking high, generally is indicative of the uphill in the atmosphere. And then the troughing here in the 50-50 low area right off the Canadian Maritime, that's going to be synonymous to going downhill. So the storm system, as it develops off the southeast coast, is going to seek the path of least resistance towards the lower pressure, this 50-50 low, and go choose that downhill path in an analogy to the bike, and not expend all the energy trying to fight this upper level ridge to the north. I like to kind of coin things in that way. Now, another great ingredient for major East Coast winter storms is an El Nino winter. Okay, this is an example of a previous storm that really got cranking. I don't have the exact storm on this one, but I just kind of want to show you what the satellite feature kind of looks like as these things get going. So we have cyclogenesis, or the development of a low pressure area storm system in the Gulf of Mexico in this particular satellite image here on the left. And you see the overrunning or the overspreading moisture to the northeast of the surface low as it's developing in the northeast Gulf of Mexico. And see how far up the shield extends, all the way up to the mid-Atlantic into Virginia and the Carolinas, as well as Kentucky and Tennessee. This is an ideal situation you look for. Okay, development, some of the biggest East Coast winter storms have started with low pressure kicking off in the Gulf of Mexico. If you look at the overall configuration of El Nino here on the right, I know you probably have seen this quite a bit of many times shared on social media, but it's very true, okay? We want a Pacific jet stream to really bring in a lot of moisture, to really go and basically the storm track is more suppressed to the south here, and then we get low pressure development off the coast. That's what we want with this type of situation during El Nino, and this is what we get during El Nino winters. Warmer and drier conditions are to the north, drier conditions in the Ohio Valley, and warmer conditions across western Canada and two parts of Alaska and the northern portion of the U.S. Jet stream placement, another major consideration for major East Coast winter storms. Okay, I'm showing you an example again in this particular image on the left, graphic on the left, showing the jet stream configuration where I've got cold air coming down from the north because of this troughing configuration of the jet stream. We have these little areas embedded within the main jet stream core that are known as jet streaks. Now, what are jet streaks and why are they important? Okay, jet streaks are areas of maximum wind speed within the jet stream itself, and they move relatively quickly through the jet core. Okay. Now, if we look at some of the graphics here on the upper right, there's a difference in the curvature of jet dynamics, the jet stream dynamics, when we talk simply about a straight line jet streak versus a cyclonically curved jet streak. So when you get troughing in that jet stream to really dig into the eastern U.S., we will get, in many cases, an example of a cyclonically curved jet streak where the main trough axis ahead of that, you got a lot of cyclonic curvature of the air right ahead of this maximum here, this max wind speed, okay? And ahead of a shortwave trough, you're going to get more cyclonic turning. That upper left quadrant, if you're beneath this DIV, the upper level divergent quadrant of the jet streak, in cyclonically curved flow, that favors upward vertical motion, rising air, and clouds and precipitation. If you, on the other hand, are back here, that would be the left rear quadrant where the CON is, the upper level convergence. That is going to be associated with sinking air motion and a quick drying out with air column. Okay, so you want to be right here on the nose of the jet stream. You want to be on the left front quadrant where there's upper level divergence and cyclonically curved flow. That's where you want to be to get the greatest upward vertical motion and rising air and heaviest precipitation with cyclone development. If we look at a straight line jet streak, kind of getting back to my analogy here, the left front quadrant is right here. Let me go ahead and draw this out so you get I'm going to label the quadrants here for you. Okay, so this is the left front quadrant. Sometimes you hear the National Weather Service use entrance and exit regions of the jet streak. That's left front, and this is right rear quadrants, okay? Whenever you have left front and right rear quadrants, that's where the air is going to rise. The air is going to rise. You're going to have your heaviest precipitation if you're at this location of the jet streak, and then also at this location. For sinking air motion and drier weather, you're really going to want to be, in this upper level convergent quadrant, the right front quadrant, as well as the right rear quadrant. That would be the sinking air motion areas. All right, so it's very important to analyze the 300 millibar chart when you're looking for East Coast winter storms to kick off. and analyze where those winds are, how those winds are within the jet stream, okay? Where the jet streak is located, the area of maximum wind speed within the jet stream. So bottom line here, I've kind of put these bullets together. The polar front jet stream, you want that diving into the eastern U.S. We want to supply our area with this cold air coming down from the north. That's a good thing to have, a good ingredient. The subtropical jet stream, you want that rolling like this, right across the south and up the coast. Okay, and then that will increase the amount of moisture, the subtropical jet, the more southern branch of the jet stream, and that will throw. A lot of times you'll see that subtropical moisture will get thrown over the top of colder air at the surface across the southeast and mid-Atlantic states. Greatest vertical lifting again is going to be in this left front quadrant. In this case, in the curved, cyclonically curved jet streak, it would be in the left front quadrant right here. You want to be in those left front and right rear jet stream quadrants of jet maxes or jet streaks. Now, let's take a look at another major component that we really want to look at 500 and 700 millibar charts. You want to look at where the placement of the shortwave trough is. Now, on this graphic on the left, it's a dashed black line. Anywhere ahead of this shortwave trough axis at 500 millibar charts or 700 millibar charts, you're going to have positive vorticity advection here, and you can have rising air motion. So you want to be generally ahead of the shortwave trough here, and you want this shortwave trough to be fairly vigorous. You'll hear TV weather people mention upper level disturbance in place of shortwave trough to make it more comprehensible for the general audience. But in general, you have upward vertical motion ahead of the shortwave trough axis, and then you got downward sinking motion behind the passage of the shortwave trough axis. In fact, there's rules of thumb for the heaviest winter precip in association or in relation to the shortwave trough. So again, air rises ahead of the shortwave trough due to positive vorticity advection. So you get PVA in this location here, and you get NVA or negative vorticity advection and downward sinking motion behind the passage of the shortwave trough axis. Usually with winter storms, once the shortwave trough axis passes your location, you're going to be back here where you get negative vorticity advection or lower values of vorticity moving in, and that's going to result in a rapid drying out of the column. Usually at the surface, you get more of northwesterly winds at this point. Here's a couple other graphics I wanted to show you. So synonymous with out ahead of the shortwave trough axis, to the east of it, this is what you have going on. You have positive vorticity advection is generally an indicator of upper level divergence. And what happens is the air spreads apart away from a single point, okay, a common axis in the upper levels of the atmosphere. And this is upper level divergence. And so that's going to promote the removal of mass aloft. And that's going to increase your low level convergence here ahead of the shortwave trough in that positive vorticity advection area. So this is where you're going to get your clouds and your precipitation to occur. Once you get the trough axis to move through, imagine this blue line here is the shortwave trough axis. You get upper level divergence ahead of it, and then you get upper level convergence behind the shortwave trough axis. That's going to result in sinking air and clearing skies. Okay. Here's another example of a vorticity couplet showing PVA, positive vorticity advection, and NVA. And this dashed black line right here through the X, this is your shortwave trough axis. Now these are vorticity values here. So my winds are going to blow parallel to my height contours on the 500 millibar chart because I don't have friction. I'm 18,000 feet above the ground. So my winds basically become what's known as geostrophic and blow parallel to these height contours, these solid dark lines. So what happens is this geostrophic wind blowing parallel to the height contours is going to blow in higher values of vorticity over a particular station, and that's going to result in increasing positive vorticity advection. And that is going to result, you see this green hashed area here? This is indicative of where the moisture in the clouds are, where the precip in the clouds are, ahead of the shortwave trough axis. Meanwhile, behind the shortwave trough axis, again, we have negative vorticity advection. We have sinking air motion in the vertical and clearer skies. So just to kind of sum it up here at the bottom, let me go back to my laser pointer. Air generally tends to rise ahead of shortwave troughs due to positive vorticity advection, where we have rising vorticity values. We generally assess shortwave troughs and ridges on the 500 millibar chart. If it's a major shortwave trough or ridge, it's going to be reflected at more than one vertical level. You may look at the 500 millibar chart, you may look at the 700 millibar chart, and you'll see a reflection on both charts. Air generally sinks in the vertical behind shortwave troughs. We have negative vorticity advection, decreasing vorticity values. General, what's important thing to think about with positive vorticity advection PVA indicates upper level divergence. Negative vorticity advection NVA indicates upper level convergence. So when a shortwave trough and PVA interact with a stalled out stationary frontal boundary at the surface, this interaction generally tends to kick off the development of an area of lower pressure. A storm is born, and as long as the upper level divergence is greater than the low level convergence, the storm will continue to deepen or intensify. There will be a point in time during the life cycle of extratropical cyclone where this upper level divergence is actually going to be weaker. You're going to have more air incoming in the low levels of the atmosphere. You're going to have more air converging in the low levels than being removed over the top of the storm. And then that's going to result in a filling air column where the pressures rise throughout the air column and the storm eventually weakens. We call those braking mechanisms of cyclones. So you want that major positive vorticity advection ahead of a shortwave trough to kind of move in. We talked about the jet stream location, the favorable areas of the jet stream for major East Coast winter storms. Now let's talk about a specific feature, really off the southeast coast of the mid-Atlantic. There is a large temperature gradient between the air over this warmer Gulf Stream. Now the Gulf Stream overall is just a very warm ocean current that moves generally like this from southwest to northeast, paralleling the east coast of the United States. And what you get is very warm air over, water temperatures here in the Gulf Stream may be 70 degrees plus in the winter. Meanwhile, back here over the land, areas of the Mid-Atlantic and the Carolinas and the Virginia, these temperatures may be on the order of 25 degrees colder than, or maybe even more than that, 30 degrees colder over the colder land associated with polar air masses as compared to the air over the warmer Gulf Stream. So what you end up having to separate the boundary between very cold air back here over the land area and very warm air right here over the Gulf Stream ocean current, we get this boundary that's known as a coastal front to set up. And this major thermal contrast between these 2 points generally will provide that necessary energy to kick off low pressure development here along the coastal front. And then that coastal front or the low pressure will intensify as it moves northeast along that boundary between very warm air to the southeast and very cold air to the northwest. In a lot of cases, the heaviest precip with nor'easters or major East Coast winter storms occurs to the northwest of this coastal front. That's where you're going to get a lot of lifting of air into the colder surface over that colder surface air. So the coastal front is basically a mesoscale type feature in the atmosphere that develops off the coast in response to a strong temperature contrast, as I mentioned, between air over the warmer Gulf Stream ocean current and colder air over the landmass over the East Coast land areas. This is often associated with cold air damming situations where you get very cold air to come down, flow clockwise around major high pressure systems over the Great Lakes, eastern Canada, and you get a cold air damming situation generally into the Virginias down to the Carolinas, and it remains generally the coldest air remains east because the air is so dense remains east of the Appalachian Mountains. And you can get explosive storm development right along this coastal front. Another smaller scale feature of some major East Coast winter storms that really piles on the snow, specifically more intense snow rates per hour, is something known as a mesoscale convective snow band. Now, these are upper level features that become favorable for mesoscale banding of precipitation. These upper level features, if they're positioned in a certain manner, will increase the low level convergence or rising air motion. This is the December 2010 storm when it was going up the coast on the 27th of December. This yellow coloring here is indicative of stronger reflectivity in decibels on the scale here on the right. And so anywhere you see this yellow banding, these are mesoscale convective bands occurring. And you can have some really heavy rates of snowfall in these mesoscale convective bands. Anywhere you see the yellow, the increased reflectivity on this radar image. And so when this occurs, you get bands of slow moving heavy snow which set up, results in highly variable snowfall rates and amounts across small areas. I've witnessed this living in southeastern Virginia along the coast. I've came back from a vacation one time in December. I drove through the Wakefield, Virginia area, right along Route 460, and there was no snow on the ground. By the time I got to Hampton Roads at the end of my journey, generally there was like 13 inches of snow on the ground. So you basically went from nothing on the ground, hardly any snow, to like a massive accumulation. And that is very common in the mid-Atlantic with these particular intense cyclones, where you get mesoscale convective bands, snow bands that set up in these storm systems. Some of the biggest snowstorms have produced these types of bands, and again, you get a very large snowfall gradient in these cases. Um, some of the biggest coastal snowstorms I've seen, the coast gets buried while 100 miles inland, like towards Richmond, Virginia area, gets next to nothing. Another major thought here, or consideration for winter storms, major East Coast winter storms, is the storm track itself. Over here on the left, by the way, all these graphics are courtesy of National Weather Service, but generally, you kind of see the different tracks. We start here on the left with the inland track of the low pressure, this red L. When the low travels inland, kind of up over eastern North Carolina to southeastern Virginia, you generally tend to get southerly winds coming up the coast, and that is associated with warmer temps, rain, and even potentially severe thunderstorms all the way up to southeastern Virginia here, because you're getting a strong low-level 850 millibar jet stream advecting lots of warm, moist air in ahead of this very intense low-pressure system. The cold and the heaviest snow is way back in here in the purple shading. Okay, that's an inland track. When you get a slightly offshore track here in the middle, that basically means the storm system, the center of low pressure, is 50 to 100 miles offshore, and now you get a slight shift. You get a slight shift of the heavy snow area. See where the purple is, and then the green area is indicative of rain. So in this case, you get more of you stay northwest of the low pressure center, the storm center, back in the colder air, but it's still, you're getting a lot of onshore winds here in southeastern Virginia, and that is going to result in some cold rain because these water temperatures off the Atlantic coast, off the mid-Atlantic, aren't quite cold enough to produce snow. And then finally, the graphic here on the right is indicative of a farther offshore track. Now these are the big ones for the coastal Virginia area and coastal Carolina, where you get cold air based on the storm track, which is more than 100 miles offshore. You get the snow in this aqua color here. See this aqua color? That indicates light snow. You get heavier snow right along the immediate coastline in the darker blue or purple. And so colder air in this case is pulled all the way to the coast, which is what you want for big East Coast winter snowstorms in coastal sections of the Mid-Atlantic. The precipitation shield is just going to pretty much remain east of I-95. Coastal regions receive significant snowfall. And this is, again, very applicable for coastal snow events across the Mid-Atlantic. So now that I've kind of broke down some of the favorable weather patterns or different features, synoptic features, we're now going to delve into the past memorable East Coast winter storms. Let's start things off with the President's Day storm of 1979. In this storm, it literally shut down New York City. It really did. Shut down New York City, Philadelphia, Baltimore, and Washington, D.C. Over a foot of snow fell with this particular storm system in 1979. And heavy snow blanketed the mid-Atlantic from North Carolina all the way to southern New York State. Dover, Delaware, look at this. 25 inches of snow for you. Baltimore, Maryland, 20 inches of snow for you. And then even Washington, D.C. had 19 inches. Richmond, Virginia cashed in at 11 inches with this particular storm. Here's some graphics, upper left, of what the cars look like in the storm. I mean, can you imagine walking out of your apartment and you know, hey, I'm going to go run to the store, be right back. Probably not so much on this day, with the snow just burying these cars back in the 1979 President's Day storm. Here are some of the prolific snowfall totals. The bullseye of heaviest snow was occurring over BWI, over the Baltimore airport, down through Annapolis, down to Pax River, Patuxent River, Maryland, and then also right across the Chesapeake Bay here in Easton and Cambridge, 20 to 30 inches of snow in that location. But I mean, this was February 18th and 19th of 1979. Look at this, 10 to 20 inches over a large swath, Harrisonburg, Luray, Front Royal, Winchester, Martinsburg, Hagerstown, Frederick, Maryland, Manassas, a large area, and even over here in Dover, Georgetown, Delaware, they also got hit pretty hard with this. Now let's move up to March 1993 superstorm. Okay, this, when I was doing meteorology school as a student, These were this was the chart set we had to analyze, the March 93 superstorm, going from the 300 millibar level all the way down through 500, 700, 850, and down to the surface analysis. This thing was a beast. Okay, I remember analyzing this in my weather school, and I'm like, geez, just to try to find the lines where you needed to plot out with the different colors was a challenge because the gradient was so tight. These lines were so closely packed. The isotherms were so tightly packed with this event with a very strong thermal gradient. And then also the isobars are very tightly packed with this particular event. This impacted a large area, this storm from Alabama to New England. And it was responsible for 200 deaths with associated cost up to $2 million. In Florida, this was interesting. The storm surge was 9 to 12 feet. I mean, think about it. We're in March. It's not hurricane season, right? But yet you're getting a 9 to 12 foot storm surge in the Panhandle area of Florida. This ended up killing 11 people, by the way. On the front side of the storm, we had 11 tornadoes which occurred, and over 1 foot of snow fell from Alabama all the way south to Alabama, from Alabama to New England. We saw record-breaking low barometric pressure from this system for many weather stations in the mid-Atlantic. Now, some of the snowfall totals were just mind-boggling. Extreme southwestern Virginia, 30 to 42 inches of snow. Now, the way the construction, the houses and the buildings are constructed, you can tell what type of snow an area gets by looking at the slope of these roofs. Like if you go up to the mountainous areas, the slopes of the roofs are generally more steep to basically allow that snow to slide off the roofs. They're not very flat. And the flatter you get with a roofing situation at any of the buildings, and it's indicative of less snow per year. You just don't want a lot of snow sitting on a flat roof because that results in extra weight and can cause collapsing. And that's what happened in extreme southwest Virginia from this storm. We saw collapsing of roofs of buildings due to the weight associated with snow. Blizzard conditions occurred over portions of northern Virginia, central and western Maryland. There were snow drifts up to 12 feet high. Snow removal and cleanup costs were estimated at $16 million in Virginia, $22 million in Maryland, and $500,000 in Washington, D.C. area. So, this was the 1993 cost estimate. Here is the stripe of heaviest snow in the blue coloring. A couple pockets of reds here in the New York State where you saw 30 to 50 inches of snow. If you see these red splotches, that's 30 to 50 inches of snow from the March 93 event. This occurred between March 11th and March 13th of 93. We did see this white stripe, this 0 to 4 inch band of snow, almost making it all the way to the southeast Virginia coast, not quite. But the further north you went, the greater the probability of snowfall accumulations along the coast of New Jersey, Long Island, as well as southeastern Massachusetts. Here are some of the snowfall totals, by the way, from this storm. 56 inches of snow accumulated at Mount LeConte, Tennessee, 50 inches at Mount Mitchell in North Carolina. You had 44 inches of snow at Snowshoe, West Virginia. This was such a whopper storm. You're thinking to yourself, hey, this is awesome. I'm a skier. I want to go skiing. And you can't even make it to the ski resort. 43 inches of snow at Syracuse, New York, and then 36 inches of snow at Latrobe, Pennsylvania. And there were 10-foot drifts associated with it in the Latrobe, Pennsylvania area. This was a satellite image in the bottom right of the superstorm. This was on March 14th of 1993. We have an explosive comma cloud signature, which is associated with some of the more intense extratropical or mid-latitude cyclones. Low pressure at this point was located off the coast of New Jersey and Long Island, with a major frontal band extending southwest. A lot of wraparound moisture with the deformation zone to the northwest of the main low pressure system with heavy, heavy snow. Now, let's turn our attention and move ahead in time to a January 1996 blizzard. Now, this began early on Sunday morning, the 7th of January. This was a whopper of a storm, a big one for Washington, D.C., in which you got 17 to 21 inches of snow. There were 30 to 36 inches of snow over Frederick and western Loudoun counties. Baltimore, you got over 22 inches of snow. And then Ocean City, Maryland, you even recorded 10 inches of snow. And those of you in New York City from the January 96 blizzard, yeah, you received 20 inches of snow. There were 8-foot drifts in New York City. Here are some of the images from that event, January 96. Look at this traffic on the left, completely snarled. Heavy snowfall rates on an interstate. You can't even see the road. The plows just simply can't keep up with these heavy snowfall rates. Look how backed up the traffic is. And then over here in the middle, we see two pedestrians crossing the street. They have some bags, it appears. Maybe they were lucky enough to find a store that was open to grab some essential supplies. But you kind of see the depth of the snow on this person's legs, almost up to the middle leg portion. So very deep snowfall at this point. And then this graphic on the right shows just a desolate scene. You know, some of the major East Coast winter snowstorms, it just completely becomes a desolate, barren, snowscape land. I mean, look at this. Just impressive. There's like nobody out. Moving ahead now to the next storm we'll talk about, and this was the February 2003 snowstorm. Now look at some of these totals with February 2003 major East Coast winter storm. All right, blue indicate, the dark blue is at 20 to 30 inches of snow in the dark blue for the area. So this is more of a northern mid-Atlantic up to southern Pennsylvania type event. It was the biggest snowstorm recorded at that particular time for Boston as well as Baltimore, Maryland. Baltimore being in here, and then Boston, of course, further up the road. Winchester, Virginia, you received 21 inches of snow, and you're generally in this location in northwestern Virginia, fairly close to the West Virginia line. Stanton, Virginia, received 9 inches, and then Waynesboro, Virginia, kind of closer to the Shenandoah Valley, received 9 inches. So, again, where was the bullseye of heaviest snow in this particular major East Coast winter storm? It was up in here. Into parts of northeastern West Virginia, pretty much all of Maryland, including Garrett County, and then up into southern Pennsylvania. Here was the surface analysis for 7 a.m. on the 15th of February. And now I'm going to really hone in on some of these major synoptic features again. Look at how strong this high pressure system is over southern Canada. It's 1043 millibar high. So we got plenty of cold air that is coming south. Now, let me draw this out. I am time to start drawing again here. Okay, so we got clockwise flow around this high, just bringing in cold air from the north. Strong northerly winds, nice gradient. You got a weak area, a stationary weak surface front located across the mid-Atlantic. And we're setting the scene for storm development at this point. Okay, 500 millibar chart here on the right for the same time period, 15 February. We're seeing a really good branch of the polar front jet stream kind of injecting some colder air and a little bit of troughing going on, which we want to see for development of major East Coast winter storms. The 16th of February now, look what happened. Okay, we had a shortwave trough. See this shortwave trough right here? It's moving over to the east, and out ahead of that, we got that positive vorticity advection. It's now kicked off a surface area low pressure, 1,008 millibar low over northern Alabama. By the way, this blue dashed line here is your 0 degrees Celsius or freezing line. Okay, anything north of this blue dashed line is below freezing temperature. So generally, you're seeing snowfall to the north of that blue dashed line. But in general, we got the positive vorticity advection, have a approaching shortwave trough in the west. We got the generation of a low pressure system developing. And then the 17th of February, that low pressure system is now moved just off east of Virginia Beach. A very intense cyclone at this point. This is your 0 degree Celsius, your 32 Fahrenheit line. Anything west of this line, up in Pennsylvania, Ohio, into northern Virginia, Maryland's all snow. And now your upper level trough has closed off into a 500 millibar close low over the Ohio Valley at this point. We're getting a lot of moisture and advection in association with the PVA. We're getting a lot of upward vertical motion, rising air at this point. All right, now, this one I hold near and dear to my heart, 18 to 19 December 2009 snowstorm, okay? Why do I hold this one so near and dear to my heart? Because I experienced it. I drove through this thing. This thing was a beast. Initially, there was low pressure, which was located in the Gulf of Mexico near the Florida Panhandle on Friday, the 18th of December. And in the meanwhile, we had colder, higher pressure, which was located over southern Quebec. So we got that funneling of cold air in from the north, strong Canadian high pressure. By Friday evening, the low pressure system then moves off the North Carolina coast, undergoes explosive cyclogenesis. In meteorological circles, we call this a bomb cyclone, in which the pressure, the central pressure, drops 24 millibars or more over a 24-hour period. Look at these snowfall totals, okay? Washington, D.C., 16.4 inches recorded at National Airport, 18 inches at Baltimore. Stuart Strath, Virginia, 28.8 inches of snow. Waynesboro, 28 inches of snow. And then Cherry Grove, West Virginia, 30. Now, I will tell you, experiencing this firsthand, driving on Interstate 64 towards Western Virginia. Things started out as all cold rain in southeastern Virginia near the coast. As I traveled northwestward, Williamsburg, I had a mix of rain and snow. West of Williamsburg, it goes to all snow. Richmond, it starts picking up in intensity. Definitely between Richmond and Charlottesville, it's really heavy snow. I'm talking maybe 3 inches an hour type rates of snowfall. And I'm literally seeing National Guard trucks pass me on the highway. You can't see the road on the interstate or the highway. It's completely covered. It looks like a country road in the wintertime. The rates were just phenomenal. Lucky that I was able to get the last hotel room right here in Waynesboro, Virginia. So 28 inches of snow. This is the most I've ever seen personally. I remember stopping at a gas station, and so this is the time in 2009 where you still have phone booths, where you had payphones. And I remember the snow almost halfway up the phone booth. I kid you not. And again, very fortunate to get to the hotel that night, get the last room in Waynesboro, Virginia. I couldn't even pull into the parking lot of the hotel because the snow was so high. Literally, a couple guys from Quebec, from Canada, get out. Now I had some essentials in the back for winter driving. I had a bag of kitty litter, in case our tires got stuck, maybe like pour it there to try to get some traction. I had a snow shovel in the back. I knew it was going to be a good snowstorm, but wow, this one was a whopper. Anyway, get the Canadian guys to help push me because I kind of got stuck a little bit. They're just having fun in the snow themselves. Push me out. I had to park on the street. I couldn't even park in the hotel parking lot. There were cars buried along the interstate road. I mean, I'm not kidding. Buried. Couldn't even see the cars anymore. There were cars buried in the hotel parking lot when I got up the next morning. Just phenomenal storm. So that's why I hold this one so near and dear to my heart. This was the surface analysis for 18 December showing low pressure developing in the northeastern Gulf of Mexico. This is a common theme for major East Coast winter storms is low pressure developing in the northeastern Gulf. You got the 32-degree line situated across southeastern Virginia through central Kentucky through southern Illinois. You got a area of high pressure here to the north over Quebec, Ontario area. It's funneling in cold winds down into the mid-Atlantic from the north. At the 500 millibar level here on the morning of 18 December, we have a major shortwave trough. It's positively tilted at this point in time. So we're starting to get positive vorticity advection and rising air motion. I'll put a plus symbol there to indicate rising air motion ahead of the shortwave trough axis. So that's starting to move over this area of low pressure. We get development of low pressure in the Gulf. 19 December, that area of low pressure has intensified drastically. Look at the pressure difference here. Probably about 1,002 millibar low at this point at 7 a.m. on 18 December, but by 19 December, it's off the Virginia coast at 992 millibars. The wind is just funneling in off the Atlantic, providing all that moisture that you want. Meanwhile, you get cold air coming in from the north like this, and you're getting some convergence of air here because you're getting colder air moving in from the north, converging with a stronger, moist fetch of easterly winds. And the bullseye is right in here where you get this convergence of air, and that's setting up those mesoscale convective snow bands. Okay. And then you kind of see what I traveled through here. See this, the blue dashed line again, that represents your 0 degrees Celsius or 32 degrees Fahrenheit, your freezing line. Anything to the west of this line is below normal or below freezing temperatures and snow. So as I traveled from the coast of Virginia and went across this blue dashed line, the freezing line, it went all snow and it was heavy. Look at the 500 millibar chart on the 19th of December at 7 a.m. Eastern time. And so we got a very deep trough. We got strong upward vertical motion occurring in this area ahead of the shortwave trough axis. And this was the satellite image of the storm. This thing was a monster. Now this was the 20th. So by this point, the storm was up here. The center of low pressure was up in that location. You had a major occluded system, and you kind of see the frontal boundary like this. And you got all this cold air just wrapping around the storm. The speckled nature of these clouds indicates very cold air. You can see where the snow was left behind in this area, still left on the ground here from the event. This was a beast of a storm. Now, this is not my picture. This is exactly the kind of thing I saw along the interstate. People had traveled Friday night, and they probably regretted it because they got stuck. Thankfully, they weren't in these cars anymore. They were out of them, but they had to come back and retrieve their car later along the side of the interstate. Just phenomenal. This is what it looked like at the hotel when I got up the next morning. These were the snow amounts right here. The dark blue indicates the true recipient of the most snow, 20 to 30 inches of snow in the blue areas of West Virginia. And by the way, the next morning I get up and I'm heading west through this. Okay. There was a major accident on the interstate in West Virginia. I basically was at a standstill for more than an hour. But you really see how the snow just ratcheted up the accumulations. This was a monster of a storm. I thought I had, maybe I didn't. Hang on a minute. Okay, now. I know where I'm at. Okay, so now we're going to move on to snowstorms. I had to get my bearings there for a minute. I apologize. 5 to 6 February 2010 snowstorms. The next one I'm going to. Now, 2010 and early February was a mammoth Snowmageddon era. They call it Snowmageddon because they were back-to-back major East Coast winter storms. The first one was 5 to 6 February. Low pressure was located just south of the Florida Panhandle. We had cold high pressure, the same theme here, centered over Ontario, stretching southeastward into the mid-Atlantic. So cold funneling of air. 6 February, deep low pressure was located east of Virginia Beach. And then this ended up being the second historic snowstorm of that magical 2009-10 winter season if you love snow and cold in the east. Here are the 2-day snowfall totals from this particular event. Baltimore, Maryland, 25 inches. Washington, D.C., National Airport, 17.8 inches. And then at Dulles Airport in D.C., whoa, 32.4 inches of snow. And by the way, that was the greatest 2-day snowfall total since 1963 at Dulles. Here are some of the analysis charts. This was 5 February at 7 a.m. Eastern Time. Low pressure forming in this, wow, right near the northeastern Gulf of Mexico again. See that? And now we got high pressure, cold air moving down into the mid-Atlantic, preceding this moisture, the green coloring here. So we got overrunning moisture on top of the colder surface air. And then we got this is an intense system because we're starting to see this closed low feature over the central U.S. And we're starting to see more of a negative tilt already to this shortwave trough axis. So we're getting some intense or vigorous lifting or rising air motion here that kicked off that low pressure system here in the Northeast Gulf. By the 6th of February, 7 a.m. Eastern Time, look where the low is now. It's a monster. 992 millibar central pressure east of Virginia Beach. You're getting colder air getting dragged down a little bit here from the northeast on the backside of that low. The freezing line, this blue dash line, is now moving further south. Anywhere north of this blue dash line here, you're all snow. The shortwave trough is now positioned in this location across the upper low is basically over eastern Kentucky at this point. Now, after the 5th and 6th of February 2010 snowstorm, we're moving ahead to 9 and 10 February 2010 snowstorm. This occurred just only a few days after you got buried by the first blizzard. High pressure settled into the mid-Atlantic region, while low pressure formed across South Texas on the morning of 8 February. And the temperatures plummeted ahead of this next storm system into the teens at most locations across the mid-Atlantic at 7 a.m. on the 9th of February. Cold air in place, ingredient number 1. High pressure to the north, ingredient number 2. Now we get 2 low pressure systems to merge over the Ohio Valley on the 8th. And you get a consolidated low pressure system, 1 main system, 1 packet of energy, very intense off North Carolina coast. And it tracks up the East Coast and deeply intensifies off the Delmarva area. Here's the surface chart, 9 February 2010. The surface chart on the left, the 500 millibar chart on the right. So at 7 a.m., what we have an area of low pressure. We'll look how strong the high is, first of all. You get this really strong high funneling the cold air in, get the freezing line at this point, in the general draped across the mid-Atlantic. Area of low pressure is developing. Very intense, strong upper level closed low over Iowa at this point in time with a shortwave trough axis extending south from it. So a lot of upward vertical motion of the Tennessee Valley at this point. 10 February, look where the low pressure is. It's off the Delmarva area, and it's very intense, about 992 millibar low. The northwesterly winds on the backside of this low pressure system are bringing the 32-degree Fahrenheit line, the freezing line, further to the southeast. Anywhere in this green shading, it's snow, and it's snowing heavy. 10 February. Pennsylvania, New York State, northern Virginia, Maryland, West Virginia, Ohio, and Indiana. And then look where the closed upper level low is located in this case, just to the northwest of the surface low across parts of West Virginia. And these were some of the snow totals from the 9 to 10 February 2010 snowstorm. Look at this bullseye. 10 to 20 inches of snow in the lighter blue. Darker pockets of blue are 20 to 30 inches of snow. And then look at this person over here. They're walking through the streets. I think this was in D.C., the Washington, D.C. area. These cars are buried on the side of the street. This guy's walking through. He's like, I'm still going to get my exercise one way or another. But look how deep the snow is on his legs here at the bottom. All right, now another major event. I was kind of bummed I missed this one for southeastern Virginia. This was a doozy of a storm. 25 to 27 December 2010 snowstorm. What we had was a strong low pressure system. We had a strong low pressure system that developed. Let me see if I can get this back here. Strong low pressure system producing significant snowfall across much of the southeastern U.S. as well as the East Coast. Snowfall intensifies across the coastal regions of the Mid-Atlantic on the 26th of December. And major metropolitan areas that were impacted by this behemoth of a snowstorm: Raleigh, Norfolk, Philadelphia, New York City, and Boston. This actually ranked as the third snowiest event all time for Norfolk and Newark, New Jersey, and the sixth snowiest event for New York City's Central Park. Northern New Jersey, by the way, received the most snow, 32 inches at Rahway. So let's take a look at some of the synoptic features that came together to really produce this monster snowstorm. We had a strong upper level ridge of high pressure building over the western U.S. So we got an amplifying upper level ridge over the western U.S. That was happening in response to an approaching upper level trough moving in from the Pacific. We had shortwave troughs embedded in the northern and southern streams. They began to dive down the backside of a strengthening ridge, moving into the northern plains by the afternoon of 24 December. So a couple pieces of energy. One shortwave trough in the northern or polar front jet stream area, another shortwave trough in the southern stream or the subtropical jet. They're kind of working, getting closer together. The northern piece of energy, that northern shortwave trough diving down the front side of the upper level ridge that's over the western U.S. The southern stream moving east. And what happens is the southern stream shortwave moves east, northern stream shortwave dives south towards the southern stream. And boom, at the surface, low pressure develops and begins moving eastward. Another common theme again, cold high pressure to the north of the system as you have that cold air funneling going into the low levels of the atmosphere, cold air advection. Early Christmas morning, the northern stream shortwave trough has allowed freezing temps all the way down at 5,000 feet to reach as far south as northern Louisiana and central Mississippi. So we got some very cold air that's spilling into the trough. Further aiding in storm's development was an upper level jet streak. We talked about jet streaks at the opening of this video presentation. Associated with a northern stream trough, we have an upper level jet streak, a faster ribbon of air within the main jet stream core. This further enhanced upper level divergence, producing vertical air motion, significant amounts of snow as far south as northern Alabama, Mississippi, and Georgia, as well as portions of Tennessee and North Carolina. So these particular areas that received the snow, no doubt, were under the upper level divergent quadrant of the jet streak, which enhanced the vertical air motion, resulting in heavier snow amounts. What happens over time now on the 26th of December, the short waves merge. They form one main amplified trough over the eastern U.S., and as this occurs, surface low pressure system then really begins to deepen significantly or intensify and move northeast up the Atlantic coastline. And then you get this advection or horizontal movement of lower thickness values behind that strengthening cyclone and strengthening western U.S. ridge. That helps the upper trough to intensify into one large upper level low, which begins to move eastward over the Appalachians. And then as this occurs, you get areas of what's known as differential positive vorticity advection, that PVA area ahead of the major shortwave trough. And you get warm air advection as well, overspreading the southern mid-Atlantic states. That warm air advection moving up and over colder air at the surface results in precipitation and cloud development, large-scale lift. And then these two strong jet streaks, the one from the northern stream, the polar front jet, and the southern stream, the subtropical jet, they merge, they set up off the eastern seaboard. You get the entrance region of the northern jet streak, so that would be the right rear quadrant of the jet streak, overlaying the exit region, the left front quadrant of the southern jet streak, over the northeast, North Carolina and southeastern Virginia, and you have a major, major winter storm on your hands. You get a lot of removal of upper level divergence and mass aloft, increasing low level converging air, increasing the rates of rising vertical air motion, increasing very heavy snow over locations such as Norfolk, Virginia. Additionally, we had mesoscale factors also in play with this particular snowstorm. As the storm moved up the Atlantic coast, you had a strong shear axis. A shear is basically just this was caused mainly by directional changes. You had more northerly winds, generally located, well, here, I'll break it down right here. Storm moves up the Atlantic coast, strong shear axis exists. When you get shear, sometimes you get additional converging air with wind coming from different directions. And that developed north of the low pressure center in the low to mid levels of the atmosphere. You got strong easterly winds coming off the Atlantic, carrying plenty of moisture inland from the Atlantic. Strong northerly winds are coming on the backside of the trough, on the backside of that low pressure system at the surface. And that convergence, let me draw it out here. That convergence, let's see here. So imagine this. So you got strong northerly winds. Let's say this is the low pressure system here. Okay. The flow around low pressure is counterclockwise like this. So what you had happen is you had easterly winds blowing to the north of this low pressure center, and you had northerly winds on the backside, strong northerly winds. So the air converged at this point due to this shear, directional shear, and that resulted in increased low-level convergence or rising air motion across a larger temperature gradient, and that resulted in those smaller scale or mesoscale convective snow bands. Here's some of the surface charts now. This was 25 December 2010 on Christmas Day, 7 a.m. Eastern Time. Notice where the low pressure is developing. Okay, we have a strong cold 1036 millibar high at this position here. And clockwise flow around it, it's bringing that northerly wind into the mid-Atlantic. Meanwhile, at the 500 millibar level, we have troughing, positively tilted trough that's developed. We got positive vorticity advection, which is going to occur right ahead of that shortwave trough axis. 26 December, look at this difference. Weak, just developed low pressure over the northern Gulf, and by the 26th of December, that morning at 7 a.m., we got a heck of a snowstorm going on. Less than 1,000 millibar central pressure off of North Carolina. We've got the freezing line all the way to the coast in this case. We have a very strong 1032 millibar high over Iowa and southern Minnesota. So the continual feed, the stronger northerly winds continue and feed the cold air into the storm. You got that easterly wind component coming in off the ocean, and that, again, that low-level convergence setting up heavier mesoscale convective snow bands to the northwest of the surface low. And look at this. Your upper level low at 500 millibars in the morning of the 26th is completely closed off at this point. Look at that. 27th of December, we got a major occluded system, less than 976 millibar low pressure system off Cape Cod. Okay, really intense. You got heavy snow bands across New England at this point. And then this strong upper level closed low situated also, it's almost becoming vertically stacked at this point in the system, where the upper low is positioned directly vertically above the surface low. But look how far south the 32-degree, the freezing line got at the surface, all the way into the northern Gulf of Mexico and all the way out to the western Atlantic. That is an impressive system. Look at the ridging here as well. I wanted to kind of indicate this is your ridge axis to the west up over central Canada. So you had a very deep trough, generally on the front side of that ridge axis. Here are some of the snowfall totals from the 25 to 27 December 2010 snowstorm. Look at this. New York City, 20 inches at Central Park. Brick, New Jersey, 36 inches. Edison, New Jersey, 32.5 inches. Norfolk, 14.2 inches. This is the third most all-time for one particular storm system. Here it is showing you the different colors and the snow rates. Southeastern Virginia, all the way to the coast, 10 to 20 inches of snow. And as that low pressure system just moved up the coast, it continued to intensify and get stronger. And so New Jersey and Long Island, New York City, you got buried with this one. You kind of see where the low pressure is at this point on this satellite image. Again, what's one of the major features we see? We see majorly cold Arctic air pouring off the East Coast in this case. You see the speckly nature to these clouds here indicating a very unstable situation as this very cold Arctic air moves over the warmer Gulf Stream ocean current here. All right, now moving ahead to, this might be my last one. Yes, it is. Okay, so I'm going to end the memorable East Coast winter storms by showing my last one, 22-23 January 2016. Snowstorm, some of you remember this very well. It was the super El Nino winter of 2015-16. A low pressure developed along the Texas-Louisiana border on the afternoon of the 21st. You got high pressure descending on the eastern U.S., providing colder air in the low levels into the mid-Atlantic with northerly winds. Low pressure moves off the coast of Georgia on the afternoon of the 22nd. Snow begins falling in the central Shenandoah Valley. On the 22nd, snow moves into Washington, D.C., becomes heavy by early evening. And then on the morning of the 23rd of January 2016, low pressure was located east of Cape Hatteras, North Carolina. Now, this one, I remember it well too. This is more of an inland mid-Atlantic type system though. So I had somebody who I worked with and he lived in Fredericksburg, Virginia. And he was trying to get back home before this storm hit. He had family back in that area, Fredericksburg. He literally was taking pictures of the storm and what it looked like. They got hammered up in that area of northwestern Virginia with this one. It was just phenomenal seeing his photos throughout the storm. Anyway, here are some of the snow totals. Washington, D.C., 26 inches. Frostburg, Maryland, 34 inches. North Potomac, Maryland, 38.5 inches. Here's the surface analysis for 22 January 2016 at 7 a.m. Eastern Time. You see low pressure developing. You got low pressure developing right over southeastern U.S. actually, over central Alabama. The freezing line is extending well south at this point. You got cold high pressure to the north, funneling in that colder air. So we got cold air preceding the system. We do have a very deep shortwave trough extending all the way down almost into the northern Gulf of Mexico with the trough axis over the central Gulf. So we're going to get a lot of rising air motion and positive vorticity advection ahead of the shortwave trough axis. It's kicked off this low pressure development. By the 23rd of January 2016, look at here, 988 millibar low pressure, intense low pressure, situated just east of Virginia Beach. And you're getting just clobbered back here into Virginia, just clobbered with heavy snow rates by this point. And you get a closed upper level low. We got a closed upper level low now by 23 January, by the morning of 23 January across the mid-Atlantic. And this is what happened. I mean, you had the biggest snows occurred from Long Island, northern New Jersey, southeastern PA, Harrisonburg, you're included in that, Maryland into West Virginia and northwestern Virginia. This was the sweet spot. And then you kind of see, I think Fredericksburg is generally right in this location, right on that border between 12 to 18 and 18 to 24 inches. Not as much snow here on the coast. There was a little bit of snow, maybe 2 to 3 inches, but the major amounts were well to the northwest. And it makes sense based on the low track. The low track is a little bit closer to the coast, so the greatest snowfall is going to be about 100 to 150 nautical miles northwest of the main low pressure system. All right, that wraps up my video, everybody. I hope you enjoyed it. Memorable East Coast winter storms. hopefully I didn't leave one out that you remember, but I couldn't cover all of them. This slide deck was about 47 slides, I believe I covered. But I certainly hope you enjoyed it. If you were a kid back in this era, where you have mammoth snowstorms, you probably really relish those memories in today's warming world that we live in. We just don't necessarily get these type of events very frequently anymore, it seems, with winters. All right, I've got much more in the queue. I'm going to be working on the development of a new video presentation. I'm going to focus that one mostly on Hampton Road cities, um, memorable winter storms for Hampton Road cities, and I'm going to kind of talk about and tie in the type of teleconnections we had for those winter storm events. So I plan to do that here with my next video, most likely. Teleconnections video I released last night. And I may get into more of the long range videos from here on out every once in a while, maybe hopefully once a week with long range forecast videos, or if something significant changes, maybe more frequently. But hope you enjoyed the presentation, and hey, everybody, enjoy your pleasant weather right now. Winter's right around the corner. Until next time, everybody, take care and God bless.